In this unit, we expand our use of inferential statistics to include hypothesis testing. Essentially, we want to test an idea or a claim based on data collected from samples. Does the mean strength of beams used in bridge construction exceed the industry standard? Did a proportion of identified objects on a radar screen meet the manufacturer's claim? Did the variability in the fill rate of a bottle filling machine at Duff Brewery change after a power outage? These are questions about overall population behavior that we might want to answer based on observations we collected in a sample, and we answer these questions with hypothesis testing. There are two components of a hypothesis test statement: the null and the alternative hypotheses. A null hypothesis is a statement about a population parameter that is assumed to be true until it's otherwise declared false. We use H0 or H0 to refer to the null hypothesis. An alternative hypothesis is a statement about a population parameter that will be assumed to be true if evidence suggests that the null hypothesis is false. We use H1 to refer to the alternative hypothesis, or sometimes HA is used. Oftentimes the word claim is used for a hypothesis test. Is the claim being made true or not? Depending on what the claim is, the claim statement could be in the null or the alternative hypothesis. We'll see what that means a little later on, but I say it now to reinforce that the claim isn't necessarily the statement that we assume to be true, the null hypothesis. We generally think of hypotheses as the null hypothesis is true unless evidence suggests otherwise. Our evidence comes from the sample that we collect, and the evidence is represented with what is called a test statistic. The level of evidence that would tell us to reject the statement in the null hypothesis, that is, to conclude that the alternative is true, is called the critical value. Beyond the critical value is the rejection region. If our evidence, our test statistic, lies beyond the critical value in the rejection region, then we reject the null hypothesis. These are a lot of words that don't make much sense yet. They'll make more sense when we do some examples, but I like to explain all these terms and concepts in a general way first. Let's motivate the idea of null and alternative hypotheses with a non-statistical example: the outcomes of a jury trial. What is the hypothesis that we assume to be true in a trial? That the person on trial is not guilty. That's a presumption until evidence tells us otherwise. If the evidence is compelling enough, if it reaches a particular level, then we reject the presumption of not guilty and assume guilt. There are two problems that we can encounter in hypothesis testing. That is, there are two ways to be wrong about our conclusions, called errors. It's not so much that we are wrong, but that the evidence was wrong. The evidence led us to an incorrect conclusion. We call these errors type 1 errors and type 2 errors. Motivating with the trial example, we encounter a type 1 error when the person has not committed the crime but is declared guilty because the evidence suggested guilt. That is, the actual situation is that the person is not guilty, but the jury declared that they were based on the evidence it was given. The second kind of error, the type 2 error, occurs when the person has committed the crime, they are actually guilty, but is not declared guilty because the evidence suggested no guilt. That is, the jury didn't reject the null hypothesis when it should have. In other combinations of the actual situation and court decision, we have correct outcomes with no errors. The jury didn't reject the null when the person on trial is not guilty, and when the jury rejects the null when the person is guilty. The jury trial makes for a good illustration, but this is a statistics class. Let's start talking about some statistics examples. In this unit, our hypotheses deal with an elusive population parameter, though later in the course we'll expand beyond drawing conclusions about a population based on a sample and address other kinds of hypotheses. Let's say we're studying a random variable y, which measures the height of college students. Not all students are the same height, so the height of any particular individual exhibits randomness. Remember that the population of college students exists, but it's really big, and it would be too difficult to contact every member of the population and measure their height. So we don't know what the mean of the population is, but we'd like to be able to draw some conclusions about it based on a random and representative sample of students collected from the population. Say that we want to know whether the mean of the population is 5'9" or not. That is, based on our sample, can we conclude that mu is something different than 5'9"? Our null hypothesis is that the population mean mu equals 5'9". We'll assume that the null is true unless evidence from our sample tells us otherwise. Let's go back to the two kinds of errors that could occur and discuss them in a statistical context. The two errors are type 1 errors and type 2 errors. In stat speak, a type 1 error occurs when the null is a true statement, but we end up rejecting the null because the evidence incorrectly suggested that we should. We can think of a type 1 error as a conditional event. H0 is rejected given that H0 is true. The probability that a type 1 error occurs is a conditional probability. Alpha is the probability that the null hypothesis is rejected when the null is actually true. Again, that means that the statement that is given in the null hypothesis, in our student height example, that the mean of the population of college students is equal to 5'9", was rejected based on our sample evidence, but it really shouldn't have been. Remember that sample means are random variables, and it could be that the sample told us the wrong thing about the population, even when we account for variability, sample size, and confidence. A type 1 error occurs with probability alpha, and it occurs when the sample led us to incorrectly reject the null hypothesis statement. Also note that the error is a type 1 error, and the probability of it occurring is alpha. The error is not alpha. We need to make sure we get the language straight. Also, alpha is the same as the alpha we use in building confidence intervals, and we'll discuss that in a bit. The second kind of error is a type 2 error, which occurs when a false null is not rejected. It's the conditional event that H0 is not rejected given that H0 is false. That is, we fail to reject the null hypothesis statement when the null hypothesis is actually incorrect. Again, it's not that we fail to reject the null, it's that the sample evidence suggested that the null should be rejected. In our student height example, it could be that the sample mean of student heights was such that it led us to incorrectly believe that the population mean is 5'9" when mu is actually something very different than that, even when we accounted for variability, sample size, and confidence. We say that a type 2 error occurs with probability beta. That is, beta is a conditional probability that the null hypothesis is not rejected when the null is actually false. Let's go back to the table of errors and correct decisions. When the null hypothesis is actually true and our evidence tells us that we shouldn't reject the null, then we've made a correct decision. Likewise, when the null hypothesis is actually false, when the population parameter is something other than what H0 states, and the evidence tells us to reject the null, then we've made a correct decision. Errors occur on the opposite intersections. A type 1 error occurs when H0 is true, but the evidence suggests that we should reject H0. And a type 2 error occurs when H0 is actually false, but the evidence tells us that we should not reject H0. Let's talk more about the rejection region. That's the area beyond the critical value, or the level of evidence beyond which we're convinced that we should reject the null. If our evidence, which we're calling a test statistic, lies in the rejection region, then we should reject the null. If the test statistic lies in the non-rejection region, then our evidence doesn't compel us to reject the null. We're not compelled to move away from the statement that we assume to be true. We choose a rejection region based on alpha, the level of significance that we want to have in the response. It's also the probability of type 1 error. That is, we assign a rejection region such that the probability that we reject H0 when we shouldn't is alpha. Or alpha times 100% of the time, the evidence, our sample data, tells us to reject H0 when we really shouldn't. When alpha is 0.05, the rejection region contains the area associated with 0.05. The smaller the alpha, the smaller the chance that the evidence lies in the rejection region. This also suggests that we're 1 minus alpha times 100% confident in our result, just like the language we used in discussing confidence intervals. Also like our discussion of confidence intervals is that the rejection region and non-rejection regions lie under a distribution like a z, t, or chi-square distribution. Let's consider random variable x to be the weight of shipping crates that leave a manufacturing facility. We want to know if the mean weight of crates is 250 pounds or if it's not 250 pounds. That is, the null hypothesis is that the mean weight is equal to 250, and the alternative hypothesis is that the mean weight is not 250. What would have to happen for us to reject H0? That is, in what way would the mean not really be 250 pounds? Well, it could be that the mean weight of the sample of crates could be significantly greater than 250, or that the sample mean could be significantly less than 250. In either case, we would conclude that the mean is not equal to 250 pounds. We depict the rejection region in this case with the upper and lower tails of the distribution, such that the sum of the tails is alpha, as alpha is the size of the rejection region. If the sample mean is close enough to 250, we don't reject the null. That is, if it's close enough to 250, we don't have reason to believe that the population mean is different than 250, given the variability in the size of the sample. But if the sample mean is far enough away from 250, we should reject the null. Here, far enough away is determined by the rejection region. If the evidence lies in one of the tails, then we should be sufficiently convinced to reject the null hypothesis. We should be sufficiently convinced that the mean is something other than 250. Why two tails? Because the mean could be not equal to 250 by being either significantly above 250 or significantly below it. If the evidence, the test statistic, lies beyond the critical values, then we should reject the null. Again, note what happens to the size of the rejection region as alpha increases. If alpha increases from 0.05 to 0.1, that is, the confidence decreases from 95% to 90%, then we increase the size of the rejection region. If the test statistic lies in the rejection region when alpha is larger, we're not as convinced of the result. Another way to think about that, if we reject the null when alpha is really small, then we probably really should be rejecting the null. If the evidence lies way in the tail, we have a lot of faith about rejecting the null. As such, when the tail decreases, our level of confidence increases. If the rejection region is small, then we have a lot of confidence in that result. When the rejection region is big, we have less faith that we're drawing the correct conclusion. Also, when the rejection region is big, or when alpha is big, we're leaving ourselves open for type 1 error. The bigger the rejection region, the more likely the evidence will fall in the tail when it shouldn't. Our hypotheses don't always have to be of the equal versus not equal variety. For example, we could collect a sample of resistors produced by a particular electronics manufacturer to determine if the mean resistance of the resistors is at least 12 ohms. That is, H0 is that the mean is greater than or equal to 12 ohms, and H1 is that the mean is less than 12 ohms. We assume that the null is the true statement unless the sample evidence tells us otherwise. And what would have to happen for us to reject the null? The sample mean would have to be sufficiently less than 12 ohms after we account for variability, sample size, and confidence. So the rejection region would have to be in the lower tail. If the evidence falls in the lower tail, we'll reject the null and conclude that the mean is less than 12 ohms. In this case, all of alpha is contained in the lower tail, as alpha is the area of the rejection region. We could also have an upper tail test, when the alternative hypothesis contains the greater than sign. For example, perhaps we want to test a diesel engine manufacturer's claim that the new line of 76 kilowatt diesel engines improves upon the best figure of 38 miles per gallon. Here, the claim is in the alternative hypothesis. H0 reads that mu is less than or equal to 38, while the alternative is that mu is greater than 38. The general convention for the hypothesized value that appears in the hypotheses is mu naught. For example, the convention for a two-tailed hypothesis test has mu equal to mu naught in the null hypothesis and mu not equal to mu naught in the alternative. Regardless of whether a hypothesis test is a two-tailed test, a one-tailed test in the lower tail, or a one-tailed test in the upper tail, you'll notice one common characteristic. The equality statement is always in the null hypothesis. We're always going to reject the null hypothesis in the tail. So the alternative hypothesis will always be associated with a statement made about the tail, not equal to, less than, or greater than. The non-rejection region always contains the mean value, so the null hypothesis contains equality to the hypothesized mean value, mu naught. Some textbooks always use equal to in the null hypothesis, but I think differentiating among equal to, greater than or equal to, and less than or equal to is more descriptive and also more accurate. Also, we've seen examples where the claim was the statement in the null hypothesis and where the claim was in the alternative hypothesis. That's why I don't like to get too caught up in the notion of a claim. You just have to translate the language of the problem you're trying to solve into statements that sound familiar to the signs in the hypotheses. For example, if we want to know if the diesel engine improves upon 38 miles per gallon, an improvement would be an increased miles per gallon, or more miles per gallon. That implies greater than 38. Being equal to 38 doesn't show improvement. Only being greater than does. So that tells us that one of the hypotheses should contain greater than. And since greater than doesn't imply equality, and because equality is always in the null, then the alternative hypothesis must contain mu greater than 38. Back to the resistor example, we wanted to know if the mean resistance was at least 12 ohms. The phrase "at least" implies greater than or equal to. That contains an equality statement, so it must appear in the null hypothesis. Say we have a set of hypotheses about the human hours required for a machining operation. The null hypothesis is that the mean is greater than or equal to 22 hours, with mu less than 22 hours in the alternative. We then collect a sample and find y bar equal to 19.4 hours. You tell your boss about this, and your boss, who hasn't had a statistics class, says, "Well, 19.4 is clearly less than 22 hours. The conclusion is obvious, that the mean hours is less than 22. But you're almost an amateur statistician, and you know better than that. You know that 19.4 is just a point estimate, and the sample mean is a random variable. You can't just boil down variability in sample size to a single point, and we want to have some confidence in the conclusion we're drawing. That's why we do hypothesis testing in the first place. We know that the point estimate isn't sufficient for drawing a conclusion about a population parameter." And speaking of population parameters, we'll talk in more detail about hypothesis testing for population means, proportions, and variances. The concepts behind test statistics, critical values, and rejection regions will become more apparent as we start working some of these very specific examples.